In 1921, Albert Einstein is awarded the Nobel Prize for Physics. But it isn't for his work on relativity. Apparently, that's too weird for the awards committee to accept. Instead, Einstein is honored for other contributions, including a paper on the nature of light. This paper ultimately leads to a second revolution in physics, only this time it's too weird for Einstein himself to accept. It's called quantum mechanics. Quantum mechanics comes out of the struggle to understand the structure of atoms. What physicists in the early 20th century learn is that in the world of the very small, the seemingly impossible is commonplace. Things don't exist until someone looks at them. We're unable to say exactly what path something takes to get from point A to point B. Uncertainty and chance are woven into the very fabric of existence. One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms. Atoms had been seen as amorphous blobs of positive charge studded throughout with negative electrons. In fact, Rutherford says, they're more like little planetary systems. All the positive charge and virtually all the mass is concentrated in a tiny nucleus, around which the electrons orbit like planets around the sun. This is the courtyard at Cambridge University, where Rutherford began and ended his scientific career. Imagine an atom this size.
If we think of that being the size of an atom, then the size of the nucleus would only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. Well, what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields.
When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now, this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms cannot exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. he had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. Would have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake. In 1926, Werner Heisenberg, a 25-year-old German physicist, comes up with a mathematical description of atoms that goes a long way toward legitimizing Bohr's view. Classical physicists remain unconvinced. Heisenberg's mathematical matrices are too complex, and the mysterious comings and goings of electrons are just too hard to imagine. Within a year, an Austrian named Erwin Schrödinger offers an alternative.
Schrödinger had this beautiful theory of the electron as a wave. It was smeared out over space and time. It wasn't a particle at all. Physicists loved this idea. We had a physical picture. We could look inside the atom. Physicists knew how to calculate with waves. They calculated waves as an undergraduate in college. They knew how waves went around and formed orbits. So the appeal of the Schrödinger picture was that it was pictorial. It was almost Newtonian. It was continuous. None of this quantum business. And you could calculate with it.
So which is it? Is matter made up of waves or particles? They seem to be complete opposites. Waves can pass through one another, sometimes canceling each other, sometimes making even bigger waves. But particles, on the other hand, bounce, smash, exert force when they meet. They can't cancel each other out.
So these two pictures clashed with each other, and they debated. And they had arguments, and they yelled and screamed at each other. In fact, one day, Heisenberg was so worried that he simply came down with hives and hay fever and tremendous case of allergies, worrying about whether or not the rival picture was correct.
In 1926, Bohr and Heisenberg invite Schrödinger to Bohr's new institute in Copenhagen to try and work out their differences. Heisenberg writes about the visit.
Though Bohr was an unusually considerate and obliging person, he was able in such a discussion to insist fanatically and with almost terrifying relentlessness on complete clarity in all arguments. He would not give up, even after hours of struggling, until Schrödinger had admitted that his interpretation was insufficient. Every attempt from Schrödinger's side to get around this bitter result was slowly refuted, point by point, in infinitely laborious discussions.
Bohr's wife nurses Schrödinger when he falls ill from exhaustion. She brings him tea and cake, even as her husband sits on the edge of the bed continuing the argument. Still, Schrödinger clings to his classical view, wearily noting at one point, if one has to go on with these damn quantum jumps, then I'm sorry I ever started to work on atomic theory.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering, how can it be? How can it be that you don't quite know where the electron is? And then in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg calls his insight the uncertainty principle. In a clear mathematical way, it says the more you know about a particle's position, the less you can know about its speed and direction. And the opposite is also true. The more you know about a particle's speed and direction, the less you can know about where it is at any given time.
And when he finally had that idea, he realized that he could merge the Schrödinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrödinger wave. So we now have this beautiful synthesis of waves and particles.
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here. And I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall or screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
According to the quantum theory, even the most bizarre events have a probability of taking place. There's a certain probability that I will dissolve and simply rematerialize on the other side of that brick wall. Now, you may say to yourself, well, that's impossible. We've never seen anyone dissolve and rematerialize on the other side of brick walls. But we actually give this problem to our graduate students. To our PhD candidates, we ask them to calculate, using the quantum theory, what is the probability that you will find yourself on the other side of a brick wall? Now, to tell you the truth, you would have to wait longer than the lifetime of the universe for such an event to take place. So you don't have to worry. Your atoms are not going to dissolve, and you're not going to rematerialize on the other side of brick walls. But there is a probability you can calculate for that event happening.
And then you can ask yourself the question, do I understand it? I don't even know what that means, understanding. I have problems with that. Physics describes things, describes phenomenon. And as long as it is predictable, as long as that formalism applied in a certain situation gives you the right answer, who cares? Who cares what the meaning is of understanding? I think I leave that up to philosophers. And I think they don't have a clue either, of course, but they... Yeah.
There are some physicists who refuse to accept that quantum mechanics represents the full story of the subatomic world. The most famous is Albert Einstein.
Quantum mechanics is very worthy of regard, but an inner voice tells me that this is not the true Jacob. The theory yields a lot, but it hardly brings us any closer to the secret of the old one. In any case, I am convinced that he doesn't throw dice.
He couldn't believe that there were big patches of the world about which we could not know. And his idea, from early on in his life, all the way to the end of his life, was that there ought to be a set of equations, deterministic, causal, ordered, formulated in such a way that they could tell us everything about a future in terms of everything about the present. And quantum mechanics wouldn't allow it. He couldn't stand that idea.
The world's greatest physicists gather in Brussels in 1927. Einstein challenges Bohr and the idea that uncertainty rules the world. Werner Heisenberg writes in his diary,
"We all stayed at the same hotel. The discussion usually started at breakfast, with Einstein serving us up an imaginary experiment by which he thought he had definitely refuted the uncertainty principle. In the course of the day, we would have discussions on the matter, and as a rule, by supper time, we would have reached the point where Niels Bohr could prove to Einstein that even his latest experiment failed to shake the uncertainty principle. Einstein would look a bit worried, but by next morning he was ready with a new imaginary experiment more complicated than the last."
One of Einstein's challenges is so clever, it has Bohr deeply concerned for the future of quantum mechanics. Physicist Leon Rosenfeld writes,
Bohr did not see the solution. I shall never forget the sight of the two antagonists leaving the hall. Einstein, a tall, majestic figure, walking quietly, with a somewhat ironic smile, and Bohr trotting near him, very excited. During the whole evening, Bohr was extremely unhappy, going from one scientist to another, trying to persuade them that it couldn't be true, that it would be the end of physics if Einstein were right.
Bohr spends a sleepless night in his hotel room before he discovers a flaw in Einstein's argument. Ironically, it involves a subtle application of Einstein's own theory of relativity.
Bohr and Einstein are an astonishing pair. In many ways, they loved each other. They loved talking to each other. They loved engaging with each other's ideas. And yet they wanted such utterly different things from physics that they never really could see eye to eye.
God does not throw dice was Einstein's unshakable principle, one that he would not allow anybody to challenge. To which Bohr could only counter, nor is it our business to prescribe to God how he should run the world. Einstein and Bohr had their last battle about quantum mechanics in 1933. By this time, both relativity and quantum theory are almost universally accepted by physicists as the most powerful ideas they have for explaining the world. Now, attention shifts to another challenge, figuring out what goes on inside the atom. Physicists want to know what holds the nucleus together. They want to know if protons, electrons, and the newly discovered neutrons make up everything in the universe, or if these particles are made up of something even more fundamental. In the process, what begins as an intellectual quest turns out to have explosive consequences. In the early 1930s, Albert Einstein emigrates to America to escape the rising tide of fascism and anti-Semitism in Germany. Before the decade ends, many of Europe's finest scientists are forced to make the same journey. Among the last to leave is Niels Bohr. He arrives in the United States in 1939, bringing with him stunning news. In Hitler's Germany, two scientists have split an atom of uranium, releasing in that moment some of the tremendous energy bound up in matter. Using simple equipment widely available, they produced the first evidence from a controlled experiment of Einstein's famous equation, E equals mc squared.
I was in Berkeley, and people had gone to the meeting in Washington where Bohr brought his news, and they called up and said, gosh, this is amazing, can you do it? And in a day or two, 2 or 3 people had done it.
No longer any doubt about it. That uranium...
I could see the big spikes of fission on the oscilloscope screen. And by the end of the month, everybody knew this was going to be a wartime device.
At a super-secret facility deep in New Mexico's scrubland, the U.S. Army assembles a team of American and transplanted European physicists, the greatest collection of scientific talent the world has ever seen. Their challenge? Create an atomic bomb before the enemy.
We were galvanized by the notion that the Germans were ahead. They had spent a lot of money, they were very good, they were just discovered in Germany, they had able people. Actually, we didn't realize that they had lost so much by destroying the community as they had done. It was lucky.
Americans have the talent and practically unlimited resources. In less than 5 years, $2 billion creates a nuclear project the size of the U.S. auto industry. Yet until the very end, no one can say for sure the product of all this effort will work.
The basic physics was known. The quantum principle was known. Relativity, E equals mc squared, was known. The chain reaction was known. But it was not known how to put it all together. So these physicists, some of the brightest minds of the world, were concentrated at Los Alamos not to discover new physics, because that was already done by the Bohrs and by the Einsteins. They were assembled to see whether or not it would actually work.
When I first brought the plutonium sphere in contact with a high explosive, I was quite scared about high explosive. And Roger Warner, who was in charge of that particular assembly, he was calm, and he said, don't worry about it. He said, you can't run very far in a millisecond anyhow, so you'll never know what happens if it goes off wrongly. It was a new world. Everyone could see that. Maybe it would bring an end to the war. That was very good, but who knows what was going to come after that? We didn't know. We should have known more than we did, but we didn't.
It was this fantastic experience of taking theories that were equations, and building something of enormous power, the power of the sun. But just like the opening of Pandora's box, Perhaps humanity was not ready for cosmic fire. Perhaps humanity was not mature enough to handle the power of the sun now being placed on the earth.